Hi everyone. We need to continue our lecture online. Well, hopefully you are doing okay with that. Let's continue our discussion about the red-black tree, and we are going to do a quick review again. And if you're confident that you remember everything we have covered last lecture, and feel free to skip this section. So, a review of the red-black tree. The most important part you need to remember is red-black tree is not a 100% different tree to binary search tree. Red black tree is a extension of binary search tree, and the biggest change will be we are going to color each of the node with either red or black color. And well, for the operations designed to guarantee that the height will be a O log n, and this is actually a big plus. Remember, the worst thing about the binary search tree is if it is super imbalanced, it always goes on one side, and then a search could be a O n. We don't want that. We want a tree with the height to be O log n, and this is the best tree we can deal with. So we have described the property of the red-black tree, and we have proved that those features or those properties guarantee that the height will be O n log n. And the next thing, we will try to describe the operations of the red-black tree. So those are the five very important properties of a red-black tree. So the first thing, every node should be either red or black. So that's the reason we call that red-black tree. And the leaves are all black. So for the leaves in the red-black tree, we have a different definition. Those are all the null pointers. So for example, I have drawn a very small binary search tree. So 5 is the root, so 3 is smaller than 5, and 1 is smaller than 3. And 10 is greater than 5, and 8 is smaller than 10. Okay, so if we just want to do an ordinary binary search tree, and that's it, right? Well, but if we are doing the red-black tree, remember, so for each of the null pointers, so for example, like this 3 has no right child. So we are going to consider this as a none. So this will be a black none here. And similarly for 1 and for 1, both children will be black nuns. And same thing for 8 and for 10's right child. Okay, this is what it means. So for all the leaves, we mean the leaf now pointers or the null nodes, and they are all fake nodes and they are all in black color. Okay, so let's continue. So the next one, if a node is red and both children are black, this should be guaranteed. This means if you have a parent to be a red node and then for both of the children they have to be black. Okay, you may ask, how about we have a red node and then it doesn't have any children? The answer is it's not possible. Okay, so well, the property number 2 says all the null pointers are black, right? So for example, if we say 8, if we say, give me one moment. Okay, so if we say the 8, if 8 is a red, if the 8 is a red and then both of the children are black, that is true. The reason is all the leaves, those 2 leaves, they are black anyhow. So as long as you have a red node and then for both of the children they are guaranteed to be black. Okay, and number 4, every path from the node to the descending leaf contains the same number of the black nodes. Okay, so if we want to color this tree, and if we just stay like this, so I'm also coloring this one red. So let's see. We have 1 as red and 8 as red for now. Okay, so from 5, if we go from 5 and all the way down to all the possible paths, what are you gonna find? So if you go this way, so 5, let me change the color. So 5, and then we go to 10, and then 10 go to this now. And how many black nodes do you count? So if you count 5, you count 10, and then this fake leaf, that is a 3, right? Okay, let me change another color. So if we want to go to 5 to 10, 10 to 8, and then 8 to this now. So in this path, how many black nodes do you count? So we have 5, we have 10, we go down, we have a red. So we don't count this red, and we go here. That is another one, right? So that is also a 3. So if you want to try that again, if you go from 5 to 3 this time, and 3 to 1, and 1 to the left side. So in this case, 5 to 3, well, that is 5 and 3, and then 1. 1 is red, and this one, this fake leaf, is also a black. So we count 3 again. So this is a cool thing about a red-black tree. So from any node and down to a fake leaf, you will count the same number of the black nodes. Okay? So the last thing is, well, the root is always black. So those are the 5 important properties. So, and then we introduce a very, very important concept, which is the black hat. That is from a node, from a node down to a null leaf or a fake leaf. How many black nodes are we going to visit? And if we enforce all of the 5 properties, and then we can prove that the height, the height of the tree, so which is the height of the node, which is h, has black height to be greater or equal to the height of the node divided by 2, and we can prove this by induction. And this also, the theorem from here is, if we have a red-black tree and we have n internal nodes, and then the height will be h smaller or equal to 2 log n plus 1. So the height will be smaller or equal to 2 log n. This means the height h is a O n. Okay, this is the important part. So this is a proof, and by knowing a red-black tree has a height to be O log n, now we can do a bunch of cool things and don't worry about the worst cases. Because even in the worst cases, to find the maximum, to find the minimum, to find the successor or predecessor, or doing a search, they will all be log n time guaranteed. So that's good. And for the insertion and deletion, they are also O log n time. But for the insertion and the deletion, they may break part of the tree properties. So we have to fix the tree later if we have to. Okay, so I'm gonna stop here for now, and then we are gonna continue our new content in the next video. Okay, see you.